Here's our first example on binding energy and mass defect. I have a nitrogen isotope consisting of 7 protons and 8 neutrons. The nucleus has a mass of 2.49077 times 10 to the negative 26 kilograms. What is the binding energy per nucleon in the nitrogen nucleus? So this example, I give you the actual equation. There's 15 nucleons, 7 of those protons, so that means the other 8 are neutrons. And we're going to look at the individual masses and then compare it to the mass of the combined nucleus, knowing that some mass is lost. That lost mass is converted into energy. One thing you really have to know, or two things about this question, we're going to find energy per nucleon. So at the very end, we're going to find the amount of energy and then divide it by the total number of nucleons, which is 15. That's one trick to this question. The second thing you always have to remember is the individual masses are always larger than the combined mass in the nucleus. And you will be given these values, the mass of a neutron and the mass of a proton. You can't use 1.67 times 10 to the negative 27. We need to be more accurate, so we're going to give you a few more decimal places in the workbook or on a test or exam for this. It's not that you have to memorize the mass of a neutron and proton to 5 significant digits. They will be given to you. So the first thing we're going to do is the mass of a neutron is going to be 8 times 1.6749 times 10 to the negative 27 kilograms. The proton is going to be 7 times 1.6726 times 10 to the negative 27 kilograms. And what we're going to do first of all is look for that mass defect. So our change in mass. That's going to equal these two numbers. 8 times 1.6749 times 10 to the negative 27 kilograms plus 7 times 1.6726 times 10 to the negative 27 kilograms. And then what we're going to do is subtract the net mass of the nucleus, 2.49077 times 10 to the negative 26 kilograms. The toughest part of this is to make sure you punch this in your calculator correctly. That tends to be the only mistake that people make. So 8 times 1.6749 to the exponent negative 27 plus 7 times 1.6726 to the exponent negative 27 subtract 2.49077 the exponent negative 26, and you get a change in mass, and it should be a very small change in mass. Change in mass equals 1.997 times 10 to the negative 28 kilograms. So there's the mass defect. This is how much mass was converted to energy. Now we use Einstein's equation, E equals mc squared. So the energy equals 1.997 times 10 to the negative 28 kilograms times 3.0 times 10 to the 8 meters per second squared. And let's find the number or the amount of energy times 3 to the exponent 8 squared. you get 1.797 times 10 to the negative 11 joules. Now the answer I'm giving is in electron volts, so I'm going to change this to electron volts times 1 electron volt over 1.60 times 10 to the negative 19 joules. So we're going to divide by 1.6 to the exponent negative 19, and you get 1.123 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 electron volts. That's still not the answer. That's the total energy, but they want the binding energy per nucleon. So energy per nucleon has one more step, and it's going to equal to that number, 1.123 times 10 to the 8 electron volts, divide by 15 total nucleons. So divide this number by 15, and you should get the 7.49 times 10 to the 1, 2, 3, 4, 5, 6 electron volts. The reason why I wanted to convert this to electron volts is just to show you this is a huge amount of energy. Huge, big numbers in comparison to what we've been dealing with in energies before. Nuclear reactions, huge amounts of energy are being released. And when I get to that lesson on fission and fusion, you'll see in comparison how much energy nuclear power has compared to natural sources like coal, oil, natural gas. This is huge amounts of energy. And it's only a tiny little mass that's being converted, but because it's being multiplied by the speed of light squared, it turns out to be a huge amount of energy. And this is why nuclear power is considered to be a good source of a lot of energy. There are some harmful side effects, but it gives you tremendous amounts of energy. So this question was asking not only for binding energy, but wanted energy per nucleon. So when you're asked that, you divide by the total number of nucleons in the reaction. And whether you leave it in joules or you leave it in electron volts is really up to you, or up to how the question and answer is written.